There's a structure so massive, it defies logic. A cable-stayed bridge stretching over a kilometer across open sea. No ground support in the middle. Only cables, steel, and engineering genius. How do humans build something like this over water? This is the full process, from the ocean floor to the final bolt. Before any steel is cut, engineers spend years studying the seabed. Marine geologists drill core samples from the ocean floor. These core samples reveal the composition of the rock and sediment below. Oceanographers measure tidal patterns, wave forces, and storm surges. Wind tunnel tests simulate hurricane force gales on a scale model of the bridge. Every number feeds into a supercomputer structural simulation. Only after all simulations are validated does construction begin. The first challenge: building deep underwater foundations. Massive steel casings are fabricated onshore in a dry dock. A caisson is essentially a hollow steel box, the mold for the foundation. Each caisson can weigh over 10,000 tons. Heavy lift crane vessels transport the casings to the exact location at sea. Diverse and remotely operated vehicles guide the caisson into position. The caisson is then flooded with water to sink it to the seabed. Once seated on the seabed, compressed air is pumped inside. Workers actually descend inside the pressurized caisson to excavate rock. This dangerous technique is called pneumatic caisson sinking. Concrete is then poured inside the caisson to form the permanent pier foundation. This concrete foundation must support hundreds of thousands of tons for over a century. Now the concrete pier towers begin to rise above the ocean surface. Climbing formwork systems allow workers to pour concrete continuously upward. Each tower can reach over 200 meters in height, taller than a 60-story skyscraper. The concrete mix for these towers is engineered for salt air and ocean spray. High-strength rebar cages are assembled and embedded in every section. Post-tension cables run through the concrete to prevent cracking under stress. As the towers rise, the stay cables are prepared onshore. Each stay cable is made of hundreds of individual high-tensile steel wires. These steel wires are twisted and bundled together in parallel. A single stay cable can carry tension loads exceeding 10,000 tons. The cables are sheathed in high-density polyethylene to resist corrosion. Internally, the cables are injected with cement grout for long-term protection. The anchorage points at the top of each tower are precision-machined steel sockets. Now comes one of the most dangerous operations: installing the stay cables. Workers climb to the top of the 200-meter tower to receive the cable end. Helicopter cranes or high-capacity derrick cranes lift each cable bundle skyward. Once the cable is anchored at the tower, the other end descends to the deck level. Hydraulic jacks at the anchor point tension each cable to precise specifications. The tension in each cable is monitored by electronic strain gauges. Now the bridge deck, the roadway itself, must be constructed. For a cable-stayed bridge, the deck is built by the cantilever method. Precast concrete deck segments are manufactured in a factory on shore. Each deck segment is shaped like a box girder for maximum rigidity. Specialized deck erection barges carry the precast segments out to sea. A launching gantry crane hoisted on the cables lifts each segment into position. The deck grows outward from the tower in both directions simultaneously. This balances the load on the tower and prevents dangerous tilting. As each segment is placed, it is connected to the previous segment with epoxy adhesive. High-strength bolts and post-tensioning cables then lock the segments permanently. As segments extend toward the midspan, the unsupported length increases dramatically. The stay cables are the key. They carry the deck's weight directly to the tower. Each new cable added allows the deck to extend further into open water. The midspan closure is the most critical and celebrated moment. The two cantilever arms must meet with millimeter-level accuracy. Temperature changes cause the steel and concrete to expand and contract. Engineers schedule the final closure during the coolest hours of the night. GPS sensors, laser targets, and precision surveying equipment guide every move. A special closure segment, the keystone of the deck, is lowered into place. Workers pour the final concrete joint in a race against the rising sun and rising temperature. The bridge deck is now structurally complete, spanning the full ocean crossing. But the structure must be equipped with dozens of advanced systems. Aerodynamic fairings are attached to the deck edges to reduce wind resistance. Tuned mass dampers inside the towers absorb oscillation from wind and traffic. These massive pendulum-like devices can weigh over 1,000 tons. Expansion joints at the ends of the bridge allow for thermal movement. These joints can accommodate up to a meter of movement in extreme conditions. The cable stay monitoring system installs thousands of sensors throughout the structure. These sensors measure cable tension, deck deflection, and tower acceleration in real time. A structural health monitoring center collects all this data continuously. Corrosion protection systems inject dry air into hollow stay cables. LED lighting systems are installed along the deck and on the towers. The deck surface is paved with polymer-modified asphalt for durability in marine conditions. Drainage channels are embedded in the deck to carry away seawater and rainfall. Now comes the final engineering challenge, load testing. Hundreds of heavy trucks are loaded onto the bridge in specific patterns. Instruments record how the deck deflects under maximum design load. The actual deflection is compared against computer simulation predictions. Every measurement is documented in the official Bridge Health Baseline Report. These baseline readings become the reference for all future inspections. Cable-stayed bridges are also among the most aerodynamically sensitive structures ever built. In 1940, the Tacoma Narrows Bridge in the USA collapsed from wind-induced flutter. Modern cable-stayed bridge decks are aerodynamically shaped to prevent this flutter effect. The deck cross-section resembles a streamlined aircraft wing in profile. This aerodynamic shaping allows the bridge to withstand winds over 300 kilometers per hour. Finally, after years of construction, the bridge opens to traffic. The cable-stayed bridge now stands as a testament to modern structural engineering. Let us now understand why cable-stayed bridges can span such enormous distances. In a conventional beam bridge, the deck must carry loads by bending alone. Bending creates enormous tensile and compressive forces within the deck material. This limits how far a beam bridge can span without intermediate supports. In a cable-stayed bridge, the stay cables redirect the deck loads upward to the tower. The tower then transfers those forces directly downward into the foundation. This means the deck is in compression rather than bending. Concrete and steel are far stronger in compression than in bending. This principle allows cable-stayed bridges to achieve spans over 1,000 meters. The Russky Island Bridge in Russia holds the record at 1,104 meters main span. The Millau Viaduct in France rises 343 meters above the Tarn River Valley. Vietnam's Bai Chait Bridge spans the Ha Long Bay with a single elevated pylon. The Stonecutters Bridge in Hong Kong has a main span of 1,018 meters. These structures are not just feats of engineering, they are icons of civilization. The long-term maintenance of a cable-stayed bridge is as complex as building it. Robotic cable inspection systems crawl along each cable checking for wire breaks. Ultrasonic testing devices can detect internal corrosion invisible to the human eye. Bridge inspection drones fly beneath the deck scanning for concrete delamination. The stay cable vibration frequency is measured to calculate cable tension remotely. Machine learning algorithms analyze sensor data to predict maintenance needs. Some cable-stayed bridges are designed to last 200 years or more. The science of keeping a bridge alive is called structural health monitoring. Every cable, every bolt, every expansion joint is tracked in a digital twin model. The digital twin updates in real time as the physical bridge responds to traffic and weather. This is the future of infrastructure, living bridges connected to the digital world. From ocean floor geology to robotic maintenance drones, this is cable-stayed bridge engineering. It is one of the greatest achievements of the human mind and hand.